In the previous section, we described the effect of VI execution modes, throughput, and latency on FPGA math and analysis VIs. By the end of this module, you will be able to use the 4-wire handshaking protocol when using multi-cycle FPGA math and analysis VIs. So in the previous module, we talked about how on the FPGA math and analysis VIs, you can either use them outside of a single cycle time loop or inside a single cycle time loop. So remember, if we were setting it to run inside of a single cycle time loop, a lot of these VIs are going to be multi-cycle, right? And we're going to get these extra terminals here. So on this slide, we see that there's the input valid, there's ready for input, there's output valid, and ready for output. Okay, so imagine this block diagram is sitting inside a single cycle time loop. Now we're just going to explain some high-level concepts about these handshaking terminals, and in the next slide we'll talk about a specific example to try to make it a little bit more clear. So in a single cycle time loop, handshaking is necessary because multi-cycle nodes need more than one cycle to compute valid data, but the single cycle time loop forces these nodes to return data every single clock cycle. Therefore, the multi-cycle nodes do not return valid data every single clock cycle necessarily, and that's due to the throughput and latency. So to ensure the numerical accuracy of an algorithm, these nodes that depend on the data must know whether the data is invalid or valid. So here we've got a handshaking protocol that you can use with certain nodes inside a single cycle time loop. This protocol involves the terminals that you see on this slide. So the first one, input valid. This is going to specify that the next data point has arrived for processing. And the next one we see there is the ready for input. This one is going to indicate whether the node can accept a new data point during the next clock cycle. Next we see the output valid. This one's going to indicate that the current data point produced by the node is valid and ready to be used by downstream nodes. And then lastly we see the ready for output. This one is going to specify whether the downstream node can accept a new data point. So let's quickly talk about this example here. So we see that there is a ready for input terminal right there, and what that's going to say is, okay, this node is now ready to accept inputs on the next iteration. This is why we're wiring the ready for input into a feedback node. So the next iteration, the upstream node knows that our VI is ready for an input. So the upstream node is going to be able to say whether it's sending valid data or not, and that's going to go inside the input valid. So if our middle node here is ready for an input and it sees that the input valid is true, it's going to go ahead and take that data and start processing it. Now let's talk about the output valid and ready for output. So the downstream node is going to let our middle node know whether it's ready to receive a valid output yet. Okay, so the downstream node is feeding that into a feedback node, and that feedback node is telling it on the next iteration, the middle node will know whether the downstream node is ready for an output. And if it's ready for an output, then our middle node will send output valid and send it a true value, as well as outputting the valid output data. Okay, so let's take a look at a practical example of VI handshaking. Okay, so here let's take a look at what we got on the block diagram. We've got two multi-cycle nodes inside a single cycle time loop. The first node we see is a scaled window. So the scaled window has a throughput of 1 cycle per sample and a latency of 3 cycles. That means the scaled window is going to be able to accept the new input every single cycle. But the latency, the output associated with each input, is going to happen 3 cycles later. Now let's take a look at the FFT one. So that is going to have a throughput of 4.07 cycles per sample and a latency of 228 cycles. So we won't get too much into that in this particular example, but you're going to see how these different handshaking terminals work. Okay, so on the chart, we see an example of what actually happens with these nodes. So let's look at loop iteration 0. Okay, so on loop 0, both the scaled window and the FFT VIs are going to have a ready for input of false. That's because it's basically doing some initialization in that first cycle. Okay, so let's go to loop 1. So in loop 1, scaled window and FFT are both going to be ready for input. So that's why those are set to true. Okay? So the ready for input is telling the upstream nodes on the next cycle that these nodes are ready for input. So let's go to the next cycle. So let's go to loop number 2. So in loop number 2, because the scaled window VI is ready for input, it's going to consume data A. Okay, so it's going to consume A, but the output valid of scaled window is still going to be false. The reason why is it's going to have to wait 3 cycles of latency before that output is going to be valid. Okay. Now let's look at the FFT node. So the FFT node is still ready for input because the output valid of our first one, the scaled window, is still false. The FFT node is just kind of waiting there for its input valid terminal to be set to true. Okay. So let's go to loop number 3. So the scaled window, because its throughput is 1 cycle per sample, it's able to consume its next piece of data. So it's going to consume B, but output valid is still false due to the latency. FFT, in the meantime, is still waiting for its input valid to be set to true, but in the meantime, it's still ready for input. So it's going to output ready for input true. Let's go to loop number 4. So in loop number 4, scaled window, again, because of its throughput, it's going to be able to consume C, but the output valid is still false because of that latency. FFT, in the meantime, still waiting for a valid input. And finally, let's get to loop number 5. So in loop number 5, scaled window, it's going to consume D, and finally 3 cycles of latency have passed, so now the output valid is true. And because the output valid is true, let's go to the FFT node. The FFT node is going to see an input valid of true, so it knows it's valid input, and it's going to be able to consume A prime. Okay, so now let's talk about FPGA loop throughput and latency. So we're going to talk about the throughput and latency for the entire loop if it has multiple multi-cycle nodes in there. Okay, so if you have a series of nodes inside a single cycle time loop, the throughput for that entire series of nodes is going to be limited by the throughput rate of the slowest node. Okay, so the slowest node technically has the largest cycles per sample, right? So if we take a look at this example, you'll see that out of all these nodes, the highest throughput we see is 4.07 cycles per sample, right? So that particular node is going to have to wait about 4.0 cycles per sample, which is going to slow down the rest of the nodes. Okay, so the throughput for this series of nodes is going to be 4.07. Okay. Now let's talk about latency. So the latency for a series of nodes inside a single cycle time loop, you're just going to add up the latency of all the nodes in your series. So in this case, we're just going to add them all up, and that's going to be the total latency for that series of nodes. Last thing I want to talk about is use caution when branching wires inside here. So it's important to consider node latency when you're branching wires. If the latency between 2 parallel branched paths is different, data along those 2 branches may not be correlated. So at this point, I would recommend that you do exercise 7.2, 4-wire handshaking protocol. These handshaking terminals, since there's 4 of them and there's 4 wires, a lot of times it's referred to as 4-wire handshaking protocol. So in this exercise, you'll be able to actually wire some of these VIs together and configure them, and this will give you a better idea of how throughput, latency, and these handshaking terminals work. So for now, let's go ahead and take a look at the solution, and I'll demo that. Okay, so let's jump into the solution for exercise 7.2, 4-wire handshaking protocol. So I'm going to open this up and notice that this VI is running on our FPGA. And let's look at the block diagram real quick. So this is the same block diagram that you saw in the previous slide. And notice that we've got a series of nodes here. Okay. So notice that there's the input valid, so all these handshaking terminals, and they're wired together in the way that we described in the slides. So some of them are going to have feedback nodes, and they're going to be wired to each other. So we just explained this on one of the previous slides with a table and kind of walked through that. But I would highly recommend that you do this exercise yourself also, so you can have some experience building it in case you need to increase the throughput of some of your algorithms inside a single cycle time loop. So for now, what I want to do is I want to talk about the throughput for this series of nodes right here. Okay, so if we want to take a look at the total throughput, what is this going to be limited by? Well, remember, it's limited by the one with the slowest throughput. In this case, the slowest throughput is 4.07 cycles per sample. Okay, so we would expect that if we were trying to calculate that, the throughput for this series of nodes, or this loop, is going to be 4.07 cycles per sample. Okay, so the way that we're going to calculate that is we've got a counter here. So this counter is going to count how many cycles or iterations that this single cycle time loop is going through. And then we have another counter here that is going to count how many valid samples we get. So notice that if output valid here is false, we're going to go to the false case and not do anything. Okay, but once the output is valid, so every time we have a valid output, we're going to go to the true case and we're going to count that, and we're also going to display it on our indicator. Okay, so based on these two indicators, we should be able to calculate the throughput for this series of nodes right here. Okay, so let's go to our front panel. Let's go ahead and run. So now it's just going to run for a bit. I'm just going to let it run for a while so we can get some bigger numbers, and now I'm going to stop it. So let's go to our calculator here. So if we take our total number of cycles right here, which is 148095, and then we divide that by the number of valid samples we got, which is 36416, we get a throughput that is pretty close to 4.07 cycles per sample. So here we've just shown how you can calculate the throughput for a series of nodes, and go ahead and do the exercise now, and you can get some experience actually building that block diagram.